Hey viewers, welcome to Science Spectrum with Don. This is the second phase of the second lectures in physical quantities. Alright, from the previous class we talked about a few things, what the fundamental or base quantities are, and of course alongside their units, their SI units, the dimensions, and we also discussed about equivalent pairs of statements regarding the English unit to the SI units. Alright, it may interest you to know that these SI units are actually defined in terms of a reference standard. So I will caption this the reference standard of SI units. Now, a unit is just a unique symbol you associate to different amounts or measures of physical quantities. It could be a small quantity or a big quantity. Alright, the meter gotten from the Greek word metron, which means a measure of something, was actually defined, that's the standard for the meter now, in 1791. The meter was defined in terms of 1/10 million of the distance between the North Pole and the equator, along a meridian that passes through France, precisely through Dunkerque in France, that passes through France. Now, one thing I would love you to take note of is, when you give a reference standard, it's simply this. You could think of this as a standard to which you could correlate units like meter to, and of course it has to be reproducible, it has to be accessible, and of course it mustn't vary. Now, along the line, it was discovered due to the Earth's rotation that this standard couldn't really make up for the meter in terms of its definition. So in 1889, the standard for meter was simply defined in terms of two engraved lines, or you could think of this as two fine lines, two engraved lines in an alloy made of platinum iridium alloy. That's platinum iridium alloy bar. Two engraved lines in platinum iridium. And of course, this is an alloy, two metals that are actually riveted together. Now, along the line, it was discovered that due to the coarseness of these fine lines, the standard couldn't really be reproducible or precise. So this was actually given up. This was given up. And of course, it stretched to the 1960. In 1960, the standard for the meter happened to be the wavelength of the red light krypton 86 atom gas emitted, and that wavelength has a threshold which is exactly 1650763.73 wavelength. So subsequent time, that was in 1960, the standard for meter was defined in terms of 1650763.73 wavelength of the orange light, of the orange red light emitted by krypton 86 atom gas, or just say krypton 86 gas. So this particular threshold was what was used in defining the meter as a standard, and of course this could not really make up for it. And then fast forward to 1967, the speed of light in a vacuum was actually gotten. And of course, in 1983, the officially the most precise, reproducible, accessible standard for the meter happened to be the interval of time, which is 1/299,792,458. This interval of time in seconds. So this interval of time, light travels in a vacuum. Happen to be the officially accepted standard for the meter. And of course, for mass also has a reference standard. Shortly before now, it happened to be the cube. It was defined in terms of a cube of water whose sides were 10 centimeter each. 10 centimeter each. Just say 0.1 meter. And of course, this was not really reproducible because when we talk about the anomalous expansion of water, you could figure out that water behaves abnormally. Then later on, the units, this standard for mass, which is kilogram, which was in terms of what it was defined in, later became the mass of a platinum iridium alloy cylinder. So it was later defined in terms of a cylinder made of platinum iridium alloy, whose height and diameter were the same. And of course, if you get a platinum iridium alloy cylinder whose height is the same as the diameter, which is 3.9 centimeter, that was the reference standard in which the mass was defined. And of course, we switched out to time. The standard for time, which was the second, how second was actually defined, happened to be defined in terms of the mean solar day. That's for time. Time, which is in second, was once defined in terms of the mean solar day. This was the officially accepted one, which is called kilogram. Time was defined in terms of the mean solar day. So in a day, you find 86,400 seconds. And what's the mean solar day? A mean solar day is simply the average time between successive arrivals of the sun's radiation at its highest point in the sky. And of course, this couldn't really make up for a standard that could be reproducible, accessible, and unvarying. So time was later defined in terms of a particular oscillation of cesium, that's of microwave. So this number of oscillations, 9192631770 oscillations of a microwave radiation, was what time was defined in terms of. So this number of oscillations of a microwave radiation could make a cesium atom, I think this is its nucleus. So when this microwave radiation bombards a cesium atom, it could excite electrons between two energy levels closest to the nucleus before it cascades down. So this was the reference standard for time, and this is the most accepted because it's reproducible, accessible, and precise. Now, temperature itself has a reference standard, that's the Kelvin, was defined as 1/273.16 of the thermodynamic temperature of the triple point of water. I mean, I really pen that down, but for temperature in Kelvin, temperature, which was the standard for Kelvin, is 1/273.16 of the thermodynamic temperature of the triple point of water. And of course, triple point of water is simply that temperature and pressure in which the three phases of water coexist. In other words, you can't really distinguish which is which. Either it's liquid, solid, or the gaseous phase of water at the triple point. And of course, the amount of substance, that's the mole, was defined in terms of its reference standard as exactly the amount of atoms you could get in 12 grams of carbon-12, roughly. This is how a mole was defined. So you take carbon-12, 12 grams of it, and you count the number of atoms. That's how a mole was defined. And of course, The electric current was defined, electric current, which is in ampere. So the ampere was defined in terms of a reference standard as the amount of force needed, the amount of force when you have two parallel conductors, thin parallel conductors of infinite length that are 1 meter apart. They are 1 meter apart. Now, these are thin conductors that are parallel to each other of infinite length. Now, when there is a constant current in each of the conductors, and that constant current could produce a force of 2 times 10 raised to the power minus 7 Newton per meter. So in every 1 meter of these conductors that are 1 meter apart, if this amount of force is generated there, that's the standard for electric current. And of course, it's precise and reproducible. Then the last but not the least is the luminous intensity, which is candela. Candela was defined in terms of its reference standard as candela was defined as in a given direction of light emitted. There was a particular radiation that was being emitted. Now, if its frequency is exactly 540 terahertz, 540 times 10 to the power 12 hertz of that particular radiation of light, that's in terms of its frequency now. And then, if in that same direction, its intensity is 1/683 watts per steradian, that is exactly the candela. And of course, having talked about this, these standards are quite reproducible and very precise. Now, SI units is preferred to the English units in the sense that it's always expressed in the powers of 10, or we call that order of magnitude. I'll give you an instance. The SI unit is preferred to the English units. An event happened in the autumn of 1999 when NASA had wanted to launch a rocket to Mars. So the unit was given in English unit rather than in SI unit, and of course, it was a total disaster to NASA. About $125 million was just lost like that, all because of differences in English to the SI units. Now we could quantify SI units in order of magnitude, or at times we call this the powers of 10. The English units are in base 16 and of course base 12, but SI units are in powers of 10. Now, when you see this, it's 9, 10 raised to the power minus 12, 10 raised to the power minus 15, I have 10 raised to the power minus 18, 10 raised to the power minus 21, 10 raised to the power minus 24. This is deci. This is the prefix deci. We attach this to different measures of physical quantities. So deci, you could use this to associate to any units you choose to. This quantifies their sizes, relative sizes. This is deci. This is centi. This is milli. This is micro. This is nano, like you hear of nanometer. This is pico. This is femto, like femtometer. This is atto. This is atto. This is zepto, and this is yopto. These are negative powers of 10. Of course, in a subsequent bulletin, I will talk about the positive powers of 10, and we'll see how we associate them with the SI units. Thank you. Please try, if you're new to the channel, to subscribe, like, and share for more content as they roll out. Thank you.